a new tool called as Laplace transform. And we saw that the Laplace transform simply provides the range of values of sigma for which the Fourier transform can exist. We have also seen an example of e power at ut, and we found the Laplace transform, and we got the range of sigma values for which the transform would exist. Let me take a similar example once again. So example, let's say x of t equals to e power say minus t ut. Let's try to calculate the Laplace transform of the signal. So Laplace by definition is going to be, Laplace transform is going to be x of s equals to integration from minus infinite to infinite x of t e power minus st dt, and I can write this directly as integration from 0 to infinite, just because the signal is multiplied by ut. This is going to be e power minus t e power minus st dt, and that is going to be equals to integration 0 to infinite e power minus s plus 1 t dt, and that is going to be equals to, now let me separate out this s. There's going to be e power minus sigma plus 1 times t and e power minus j omega t dt. Why? Because we know this s is sigma plus j omega. So this is going to be this equals to, you can see that this expression is going to be e power minus sigma plus 1t times e power minus j omega t upon s plus 1, and the limits here are 0 and infinite. And now if we attempt to replace these values, this means if we try to replace this t by infinite, we may see that this expression is going to converge only if this sigma plus 1 is a positive number. That means, let's suppose if I try to replace these values here, so it is going to be 1 upon s plus 1 e power minus sigma plus 1 times infinite and e power minus j omega times infinite. So upper limit minus the lower limit. So if I replace that with lower limit, so it is going to be minus sigma plus 1 times 0 e power minus j omega times 0. I can see that this term here, this term is going to be 1, this term is going to be 1. Yes, I missed a minus sign here, so this is going to be minus. and this term here, this complete term, this term here is going to be finite, or it is going to be non-infinite only if this sigma plus 1, this term here, is positive. So we want this term, this sigma plus 1 must be positive. Why? Because only in that case this expression is going to converge, and we are going to get some expression here that is going to be 1 upon s plus 1. Otherwise we are not going to get any expression, and this complete expression is going to tend towards infinite. So what I will write it here is, this is going to be equals to 1 upon s plus 1 and this expression is true only if this sigma plus 1 is positive, or we can say that this sigma is greater than minus 1. This is an important condition. The other terms will vanish, so this term is going to vanish, so it is going to be only if this term, if it is positive, this is going to be 0, this complete term is going to be 0. So I'll write that this complete term here is going to be 0 if this sigma is greater than minus 1, or sigma plus 1 is positive. Then only we are going to get this expression, otherwise we may not get any expression. We are not going to get any expression for this. Now this value here is actually the range of values of sigma. This is also called as region of convergence. That means these are the set of values of sigma for which this integration, that means the Laplace transform, is going to converge. So let me write that. This is called as the values of sigma for which the Laplace integration converges or we may say that the Laplace exists I should say range of values those values are called as region of convergence. Now I'll explain why it is called as region of convergence. Or ROC to abbreviate. Now as we have got here the range of values of sigma for which this integration is going to exist, the values that we have got is sigma greater than minus 1. Now if I try to visualize this sigma as a 2D plot, we can see that this s here, we know this s is a complex variable, that means sigma plus j omega. So let's try to plot this s variable in a plane. So what I mean by that is, let's suppose I draw an S-plane where this S is a complex plane, where this horizontal axis is sigma and the vertical axis is j omega. Then we may have different values of sigma horizontally, so we may have this values, say these values are, you may see these values as, let's say, -1, let's say -2, and so on. Let it be 1, 2, and so on. And here, as we have obtained a range as sigma greater than -1, you may see that anything greater than -1 would converge this integration, or would converge this Laplace integral. So I'll indicate that with a graph something like this, so I will draw a line here, and anything greater than this, so I'll draw that as like this. So anything greater than -1, I'm indicating that with this shaded region or shaded portion. This indicates the range of sigma values all greater than -1. So this range is called as the region of convergence, just because it is covering a region in an S-plane. So that's why it is called as a region of convergence. This is called as the ROC, or region of convergence. Region of convergence is simply a set of values of sigma for which this integration, or the Laplace integration, exists. So the complete expression for the Laplace transform, that means x of s, is 1 upon s plus 1 with ROC. Now that is how we should indicate, with ROC sigma greater than -1. So that's how we should indicate any expression or any Laplace transform of a signal. This is the complete expression. So while indicating a Laplace transform, we should not forget to indicate the region of convergence, because it is only those values of sigma for which this expression exists. Let's take another example. Say for example, this x of t, let it be minus e power minus t u of minus t. Let's consider this signal. Now how does this signal look like? Because last time we have tried plotting the signal, so let's try to visualize this signal. So this signal would look something like this. Here this e power minus t, that is going to be like this, is getting multiplied with u of minus t. That means it should be left hand sided signal, and of course an inversion there. So it is going to be something like this. It's going to be -1. What is this? This is x of t. It's a variable t. It's x of t. Now let's try to calculate the Laplace transform for the signal. So it is given by, so Laplace transform capital X of s is given by integration minus infinite to infinite. We know from this definition of Laplace x of t e power minus st dt, and that is going to be equals to, now integration will be from minus infinite to 0. Just because this is multiplied by u of minus t, the integration lies from minus infinite till 0 is equals to e power minus t e power minus st dt. So this is going to be equals to, so x of s is going to be integration from minus infinite to 0 e power minus s plus 1 times t dt. Now we can solve this as integration is going to be e power minus s plus 1 times t divided by this minus s plus 1 factor, and the limits from minus infinite to 0. We should be careful while replacing these limits. We cannot directly replace these limits here in t. So before replacing these limits, we should separate out this real part and imaginary part of s, so that we get a clear view of what is happening. So it is going to be sigma plus 1 times t e power minus j omega t divided by this minus s plus 1 factor, and this limits of t going from minus infinite to 0. Now we can replace these limits. It is going to be e power minus sigma plus 1 times 0 and e power minus sigma omega times 0 minus e power minus sigma plus 1 times minus infinite, so I'll write it as plus infinite here, times e power minus j omega times minus infinite, so I'll write that like this, and whole divided by this minus s plus 1 factor. Now have a look at this expression that we have obtained. Now this factor, the first one here, is e power minus sigma plus 1 times 0. So anything to the power 0 is going to 1, give you 1. So this is going to give you 1. What about this? This is again going to give you 1. Sorry, this is going to give you 1. Now what about this? This factor here, I'll mark that. This one here. Now this will tend to infinite. This is going to tend to infinite if the sigma plus 1 is positive, but we can make it converge if the sigma plus 1 is negative. So I'm missing a minus sign here, so this is going to be minus sign here. So minus minus will become plus here, so I'll remove this minus sign. Yeah. So you can see that this factor here, the whole term is going to converge, or this expression is going to exist only if this sigma plus 1 is negative. Then only this e power, some minus power to the infinite, is going to be 0. And we may get an expression as 1 upon s plus 1. In any other cases, we are not going to get this equation, or this expression is not going to converge. So this is going to be equals to 1 upon s plus 1, because this expression converges only if the region of convergence here is this sigma plus 1. This must be negative. That means sigma must be less than minus 1. Now this is the region of convergence for this signal. Now let's compare this result with the previous one. So in the example 1, you can see that this was the first example that we have seen. We may observe that the expression for x of s remains the same, 1 upon s plus 1. As you can see, the expression for x of t, that is e power minus t u of t, is 1 upon s plus 1, and for the expression, the signal minus e power minus t u of minus t, again the expression remains the same. But the change that you can see is this region of convergence, or the values of sigma for which the expression converges. For the previous case, as you can see that the sigma was greater than minus 1. But for this case, this is sigma is less than minus 1. So the region of convergence looks something like this. I'll draw this as this. Let's suppose this is minus 1. Let this be minus 2 and so on, this being 0. I'll draw the region of convergence as less than minus 1, so I'll simply draw a line here. Passing through minus 1, and I will indicate that as a shaded region. So this is the region for which this Laplace is going to converge. So this is going to be the region of convergence. So the complete expression for x of s for this new signal is 1 upon s plus 1. But ROC here, region of convergence, is this sigma less than minus 1. That is the complete expression for the Laplace transform. So as you may compare both of this signal, the first signal that we have seen was this e power minus t u of t. Now I didn't draw the visualization. This signal looks something like this. So this signal, if I try to plot, it looks something like this. So this is x of t. You may see that for this signal, that was e power minus t u of t, the Laplace transform was 1 upon s plus 1. And also for the new signal that we have seen, x of t equals to minus e power minus t u of t, it is completely different signal. And we are getting the same Laplace transform here. But the only difference is there in the region of convergence. As you may compare, for the previous case, the expression that we have obtained was same, but with the region of convergence sigma greater than minus 1. And for the new signal, we obtained the same expression as 1 upon s plus 1, but with ROC as sigma less than minus 1. So this indicates that two different signals may have the same expression for Laplace transform. However, their region of convergence are going to be different. So that's the fact that we would like to emphasize here. This Laplace transform for two different signals can be same, but the region of convergence has to be different. So no two signals may have the same set of the Laplace transform expression and the region of convergence. We shall see more into this in the next module.